Howdy, y'all. Thank you for coming. Okay. Guys, you'll be shocked to hear 35 minutes is not enough to cover an entire term's worth of math, so this will be unstructured and somewhat chaotic. Just be warned. Okay, welcome to the last one of these.
Yay.
Yay, indeed. You think, oh, I was right.
I'm so sad.
For full mark. Okay. Yes, I'm reading your anonymous stuff still. And someone asked a really momentous question. I think Lord of the Rings is better than Game of Thrones, for the person who asked that question.
Sorry, no, I didn't mean to.
Okay. Okay, one, you've got assignments due today. Again, we've moved it back/forward to 11 p.m. So if you want to ask questions, Let's do it at 11 p.m., not 4 p.m. And yes, there's tutorial today, so if you want to ask me after that or during that, feel free to do so. You have a final exam, which you'll be surprised to hear, on that day, at that time, in that place. Check the final exam schedule, Google it, look it up for all your final exam needs. Be aware that the pack is undergoing renovation, so please make sure you go to doors that might actually open. Make sure you follow the calculator rules, which will be more strict than they were for the midterm. Yes, ma'am?
I just want to ask, do you mean by pack, you mean pack gym or pack like AA? Because there's a difference kind of, like, depends on like if you have
AA?
walk.
It'll tell
Like
you
Alcoholics
what
Anonymous.
policy.
Okay.
Yeah, the gym, yeah, on the floor of the, yep. The
Yeah.
floor of the gym or upstairs, depending on where the location is.
Yeah, but like now they added like a paragraph and then like something.
Yeah, exactly what you need to do to get it.
All right, make sure you check the calculator rules. They'll be stricter for this than they were for the midterm, okay? Because you know what integrals and derivatives are now, and we might ask you for those, and we don't want you to just punch that into your calculator and get a 3 and then write the number 3 down, okay? So again, check the calculator rules. Don't bring anything illegal. Don't bring anything illegal generally. Make sure you bring ID. Make sure you follow their stupid rules on what color bottle you're allowed to use. There's people who go around the pack whose job it seems to be to hassle people. So, you know, if you're okay with being hassled, fine. If you're not okay, make sure you follow their rules. I'm okay with being hassled, so. Your seating is going to be assigned again, so check Odyssey, as you did before, to see where in the gym you'll be sitting. There are a lot of you. Okay, check Odyssey, and I think the seats are assigned even now. You're allowed a cheat sheet, letter size, 8.5 by 11 inches, both sides, handwritten. Please follow that rule. Okay, handwritten. Okay, the vast majority of this thing should be post-midterm material. There will be some pre-midterm material. A, because you need to know what a function is to be able to integrate one. And B, it'll be tied into other stuff. So you remember when we did curve sketching, for instance, you needed stuff from before the midterm to be able to sketch a curve. So some of it will be tied in with other stuff. Some of it might just be from pre-midterm. The vast majority should be post-midterm. Okay? So don't just outright neglect the stuff from before. Someone asked me for cheat sheet suggestions, and I guess my suggestion would be learn everything and don't even need a cheat sheet. Yeah, so honestly, any steps you're worried about forgetting, so if I gave you a recipe or something, or if you cooked up your own recipe and you're worried you'll forget a step, like, I don't know, in the substitution thing, you might forget to change the limits around, write that down, color it pink, do whatever you need to do to make sure you don't forget. If there's common derivatives and antiderivatives you're worried about slipping up on, for instance, you get an antiderivative backward, you might do the power rule backward or something like that, make sure you write stuff like that down, whatever it is you might slip up on. What I'd advise you, and you can put whatever you want on there as long as it's handwritten, you can put sample problems on there, whatever you want. try to avoid filling it up with just finicky technical crap from the slides, okay? The slides were there to support, not all of those details are important, okay? We're not expecting you to write things the way math majors write things, so, you know, don't fill it up with finicky technical stuff you've never used or seen. Make sure you understand the stuff. Make sure your cheat sheet's actually useful to you in case you're gonna use it, okay? Okay. You can expect me to have some sort of office hours at some point. I'll announce those. Review sessions, I believe, did you guys get an announcement? Yes? Okay, I think those are the review sessions. So go to those if you're interested in that kind of thing. Practice material should be posted, by which I mean old exams and that kind of thing. You'll notice that, and also there's also problems from textbooks and stuff you can do. Old assignments you can work on. Come see me if you need more stuff. What else do I want to say? When you do the previous exams, realize that there's some stuff they did that we didn't do, okay? So if it's talking about, you know, volumes of solids of revolution and stuff like that, you know, you can do it if you want, but we won't test you on it. Stuff like indeterminate powers, okay? So where you've got, it's an indeterminate form where you've got something to the something. So some of them might look like that. You don't need to know those either because we never talked about them. And we don't test you on stuff that you never were exposed to at all. And again, please don't get caught up in trivia or insane cases or technical garbage, okay? Try to understand the big picture, try to understand what you're doing, practice a lot, understand, check, and ask if you have any questions at all. Okay? Okay, people, this is a good time to ask me, are we going to be tested on this? Should I bother studying this? That kind of thing. If you want to ask me that at any point, now is a good time to ask me. Ask me anything you want right now. Give me a way to fill up this time. Yes, ma'am?
Are we allowed calculators? Because some people have been saying different things about it.
Like not calculators at all?
Yes.
Those people might be intoxicated.
Okay.
You should be allowed calculators, nothing, yeah. Follow the rules and you should be allowed calculators. Cool? Sir, yeah, go.
You learned something called logarithmic differentiation.
I did one example in tutorial and you won't be tested on it. You will not be tested on logarithmic differentiation. Okay, sorry, logarithmic differentiation is not derivatives of logarithms, okay? It's a special technique for differentiating things, okay? So the special technique of logarithmic differentiation you won't be tested on, but the idea of what's the derivative of logarithm, that's fair game. At the back? Yeah.
So what's the weight of pre-midterm?
Say again?
What's the weight of the pre-midterm? Like,
Yeah, I was worried about that.
First half of the term, how the weight could be, and how much percent will be in the final?
You want a number, huh? Not a ton was going to be my actual answer. I don't have a percentage. If you need a percentage, I can try to cook up a percentage, or we'll tell you, we'll tell everybody. Okay, again, some of it's baked into the advanced material. You need to know what a function is. There will be standalone stuff. If I say anything, you might hold me to it, so I'm not going to say anything. Not too much, okay? The vast majority is other stuff, but there is some that is pre-midterm, okay? Okay. Dedicated pre-midterm. Yes, ma'am?
Do they post like a sample like final that we can do?
They
on
posted
there?
like 4, I think.
Okay, yeah, sorry. I just
We posted 4, I think. Yeah.
For the graphs, like what, like how many graphs are there?
Say it one more time.
For the graphs on the exam,
Mm-hmm.
like what kind of graphs do we need to know for it?
What are we talking about?
Like curve sketching is
Is this late curve sketching or the stuff from before where you transform things?
like the whole.
Okay,
like
being
everything.
literate about how you transform a function is a good thing. Okay, so we talked about some things before. That would be good. Okay, so don't be completely oblivious to that stuff. By which I mean, what effects do stretches and compressions and translations and those kinds of things have? And what do they mean for certain functions? That would be good. Later curve sketching, we did curve sketching in tutorial. I think we just did one example, and then I gave you another one to work on if you wanted to. Curve sketching brings together a ton of stuff, okay? So if we ask you a curve sketching question, we will hold your hand through it. So we'll say, okay, find intercepts, find, you know, symmetry, find this, and then bring it together and give me a sketch. Okay, so it won't be sketch this period, it'll be find these things and then use them to sketch.
Okay.
Is that fair?
Yeah.
Okay. Okay? Yes, Han, hello.
Is there a big emphasis on word problems?
There will be some word problems. By the way, I heard the same problem complained about by two people, which is on your assignment, and I think is about something like energy or work done to lift a mass or something
Oh,
like
yeah,
this with
that's-
gravity involved. Okay, that's not really much of a word problem, guys, because all that says is evaluate this integral with a paragraph of text around it. Okay? So don't be scared of word problems. First of all, one of the reasons word problems turn up at all is because we want to excite you and give you things that actually mean something in the real world. Otherwise, it's just a load of practice, just exercise. So part of the point of word problems is to give you context and to tell you this thing actually means something, this integral actually means something. And some word problems actually get you to model a bit, okay? And we don't go nuts about that, but we ask you to model a bit, like the optimization questions, the related rates questions. You have to come up with an equation and take a derivative or do something like that. Okay? So, there will be some. It's not the entire test, but there will be some. A decent proportion. If you're all looking for numbers, you notice I'm not giving you numbers because I didn't calculate them. But yeah, be prepared for some word problems. That would be a good thing to do. Yes, sir.
Is there a Riemann sum?
Okay, my answer to that Riemann sums, my answer to that right now is know what a Riemann sum is, be able to do one, be able to do that stuff a couple times, okay? Don't emphasize it, don't waste all your time on it, and that's all I'm saying right now, okay? Yeah. Okay, so technically Riemann sums is in the thing, but I would not kill myself and lose time working on other stuff to try to practice that. Is that fair? Okay.
It's
If
Newton's.
there's anything more definitive to say, we'll say it. Yeah.
What about the Newton's method and the bisection?
It's game. Yep. It's possible. It's possible. Okay? We won't ask you to do 60 iterations of something, you're not a computer, right? So, yeah. And the stuff at the end of Newton's method, where this is when this doesn't work, all that stuff, you don't have to worry about that stuff, right? I said we wouldn't test you on that, so we won't test you on it. Okay, you remember the stuff at the end, those special weird cases where Newton's method fails? Okay? All right, keep asking me anytime you have questions. Okay, what am I gonna do? All right, well, I could just go through this thing. Okay, if I don't see your hand, just shout at me, okay? Okay, what I'm gonna do is I'm just gonna quickly go through this, and I'm gonna say things, shockingly. I have some other comments, I might be able to do a problem or two. And that's that. If you have any questions, just say, okay? And if you feel this format is upsetting and you want to leave, you can leave anytime you want. Okay. Right from the top, okay? We started talking about functions. You should be literate about functions. You should understand what a function is. You should be able to understand the properties of functions. We talked about solving equalities and inequalities. You should have noticed why more recently, okay? Especially when you're talking about things like critical points. You needed to solve stuff. You needed to see when something was negative or positive. That kind of stuff all matters. In terms of sketching functions, again, before what did we learn? We learned how to transform a graph of a familiar function, and then later on we saw how to use derivatives and limits and intercepts and symmetries and all that stuff to graph something we didn't recognize. Okay, we talked about various ways of combining functions algebraically, also compositions. We talked about flipping a function around and getting its inverse. I'm not going to repeat that. We talked about exponential functions and logarithmic functions, and they came up later again when we talked about exponential processes, and we talked about exponential convergence and all that, so that's all possible. We talked about trig, and then we talked about derivatives of trig things, and we did integration with trig things, so all of that is fair. We then moved on to limits and limits of sequences, which didn't turn up much, except when we wanted to deal with Riemann sums. So when we wanted to define the definite integral, we needed to talk about the limit of a sequence. So that's when that came up, again. We motivated a lot with instantaneous velocity, and then we moved on to the limit of a function, and to be able to talk about the derivative. You remember with the limit of a function, there were a lot of different cases, there were a lot of different methods you could use. You remember, multiplication by radical conjugates. You may remember factorization and canceling. You remember sometimes you can just plug in. Later on, we learned L'Hopital's rule. Okay, so there's a lot of methods for dealing with limits. So you should be able to, if you see a limit, figure out what the heck to do. Okay, so don't just haphazardly try methods. Do enough that you can recognize a pattern and pretty smoothly get through it. Okay, remember that limits let us define continuity, and remember that when we recognize continuity, we could use that to evaluate a limit. So if a function is continuous somewhere, you can get the limit by just plugging in. And you should be able to know how to recognize continuity, okay? So when you have a combination of functions, first of all, know what the basic continuous functions are, and we have a lot of continuous functions in science. Be able to combine them in some way, algebraically, composition, so be able to recognize that something is continuous, and so you don't have to worry about certain things. Remember that both the derivative and the integral are defined as limits. But once we learn those definitions, how often did we really use them? Remember, once we learned the derivative, we could use L'Hopital's rule to evaluate certain kinds of limits. Remember not to use L'Hopital's rule when you're not allowed to. L'Hopital's rule is to be used for certain classes of indeterminate forms. Okay, so when you have a 0 over 0 indeterminate form, when you have infinity over infinity indeterminate form, then you can use L'Hopital's rule. Don't just use L'Hopital's rule because you feel like it, you might get a wrong answer. Okay? Also remember we talked about various kinds of indeterminate forms, so not just quotients, but also products and differences. All of that's fair game, and most of that was in tutorials. So if you don't know what I'm talking about, look at differences, look at products, and quotients for indeterminate forms. More on limits. You remember that one of the three approaches we talked about when we were trying to optimize functions that were continuous but not on a closed domain. One of those involved limits. You just may see that in your notes. That wasn't a hint. You may see it in your notes. And finally, you remember in curve sketching, when we were trying to sketch curves, we talked a lot about asymptotes. Asymptotes matter, and asymptotes are defined in terms of limits. So limits are important, guys, in calculus. And they're kind of the bedrock for the whole thing. Just a word on asymptotes here. Judgment Day. Okay. Again, this is all chaos, it's all, disordered. If we have something like that, if we have something like that, we can factor it, you get x squared minus 4, and the difference of squares there. Similarly on the bottom, I may have screwed this up. Okay. Okay, factor on x, we get x squared minus 4, difference of squares, x squared minus 1, difference of squares. Okay, there we go. So if we give you something like that and we ask for asymptotes, two kinds of asymptotes, there's horizontal, there's vertical. Okay, horizontal is talking about do you approach a horizontal line as you go that way or as you go that way. And you may remember for stuff like this, we talked about how to do those kinds of limits. Limits at infinity. For rational functions, what do? You divide by the highest power in the denominator. You go through and you evaluate the limit. So we talked about that quite a lot, and that was pre-midterm, we talked about that. For vertical asymptotes of something like this, you should be suspicious when you look at zeros of the denominator, okay, for a rational function. So look at the zeros of the denominator and suspect those to be vertical asymptotes. So for instance, x equals 0, x equals minus 1, and x equals 1. One of those is not a vertical asymptote. Which one is it? 0. The universal guess. 0, okay? And this kind of cancellation is a signature of something that you might think is a vertical asymptote, but isn't. Okay, so in this case 0 just winds up corresponding to a hole. The asymptotes are at minus 1 and 1. When you're dealing with asymptotes, what do? You look what goes on either side, you take limits on either side. Does it blow up, does it blow down, does it behave differently on either side? And we did examples of that, and that helps you sketch things. Also, when we got to derivatives, when you take derivatives, when you look at what the derivatives look like on certain intervals, the derivative should agree with what you think the asymptote is doing, okay? So if you think the asymptote's doing something like this, and then you do the derivative analysis and you find that the function is decreasing here, you've got a problem. Okay, so things agree with one another. Other places where we saw horizontal asymptotes, the arctan function, exponential functions. So you should be familiar with what things do as you go that way and that way. Okay, exponential functions in particular, right, have that obvious sort of decaying, and the growing ones sort of decay if you go backward. What else? Okay, this is one situation where you have vertical asymptotes. I want to shout out another one. Vertical asymptotes.
1 and -1.
For this, yeah. But like, what other than a division by zero type situation gives you a vertical asymptote? What graph did we see that definitely had a vertical asymptote? Log is good, yeah. By the way, tangent has vertical asymptotes. Why? Because you'd be dividing by zero at certain points, right? So when the tan has vertical asymptotes, it's because cos is zero. And then that's right, log. Excellent. So you remember the log function looks like that. So it sort of blows down as you approach zero from the right. So if you had something like this, log base anything dignified. Okay, so if you had something like that, that would have vertical asymptotes too, okay? Okay, because log has vertical asymptotes. Okay, again, log looks like that. Okay, and it blows down as you approach zero from the right. Okay, this inside bit looks like what? It has zeros at 0, -1, and +1. It goes that way, so it looks like this. Roughly. Okay? Remember, log is only happy when you give it a positive number. Okay? Remember that even root functions can only take non-negative inputs, log can only take positive inputs. Be aware of generally what the domains of things are, never divide by zero, so understand how domains work and how to combine them. In this case, again, this guy has to can only take positive inputs. So where's this guy positive? It's positive here, it's positive here. Okay, so that tells you where the domain of this thing is. And as the argument of log approaches zero from above or from the right, however you want to think about it, then the log blows down. Okay? So here we're approaching zero from above, okay, as we approach 1 from the right, and so the whole thing blows down. Okay, and again, we have vertical asymptotes here as well. Okay, we're approaching 0 from above in either case, as x approaches 0 from the left or -1 from the right. Okay, so again, you get vertical asymptotes when you got divisions by 0, and also log spits out vertical asymptotes. Any questions? Okay. Again, that was all limits, and we talked about limits quite a lot, and I spent an entire lecture, I think, doing stuff with infinities. Then we talked about continuity, and we talked about how to define continuity in terms of limits, how to recognize continuous functions, combinations of continuous functions. You remember the example of the wall and the temperature being continuous through the wall, okay? How do you set the parameters to sort of hook up the temperature function so that it's continuous? We then talked about the intermediate value theorem, okay, a property of continuous functions, which basically told us that continuous functions can't jump over horizontal lines, which is what you'd expect because they're all like that. Okay, we used intermediate value theorem to help find roots using the bisection method. For example, okay, if you want to solve a thing like that, that's hard to solve, okay? I don't know how to solve that exactly, so what do? You sort of rearrange it. You rearrange it and you say what? The solutions of this thing are exactly the zeros of this thing. So you're really looking for zeros of something, okay? And bisection lets you do that. An intermediate value theorem gives you a place to start and tells you and lets you motivate or justify the bisection method. Okay, for example, suppose you wanted to show that there was a 0 between -1 and 0. Okay, so if you wanted to show that there was a solution of this or a 0 or a root of this between -1 and 0, what do? You evaluate this thing at -1, and it winds up being negative. You evaluate it at 0, it winds up being positive. Okay, and then you say intermediate value theorem tells me that at some point I have to have crossed 0. Why? Because this is what kind of function? Which is? So when can you use intermediate value theorem? It's continuous on a closed interval, that's right. Okay, so it's continuous on the closed interval from -1 to 0. Okay, this thing isn't continuous everywhere. Where is this thing discontinuous? Thank you, excellent. Okay, yeah. Okay, this thing has discontinuities wherever 10 gets upset, and 10 gets upset at pi over 2 plus integer multiples of pi. Okay, so things have conditions, and some of those conditions do matter, and I think in some of the practice tests you'll see that come up. So again, you use intermediate value theorem when you've got a function that's continuous on a closed interval, so actually be able to diagnose that kind of thing. Okay, if you want to refine your idea of where the root is, you can use again the bisection method. You just narrow down by using the intermediate value theorem essentially a few times in sequence. If you have any questions or want an example of that, let me know. We also have Newton's method, okay, which relies not on continuity and intermediate value theorem, but on differentiability and linearizations. Okay, so those are your two big root finding methods. Okay. We talked about the derivative by talking about Saruman throwing the rod for the 100th time. We defined it in terms of limits. We talked about points of non-differentiability. Okay, so we talked about various kinds of non-differentiability. What did we talk about? We talked about corners and kinks. We talked about cusps. It's almost a cusp. We talked about vertical tangents. Points of discontinuity. Okay, all of those things make a function not differentiable there. Okay, so be able to recognize that, be able to diagnose that. So the higher order derivatives and what they mean in certain physical contexts. We did differentiation rules. We didn't have to do the limit thing every time, including the chain rule. And we did implicit differentiation. We applied implicit differentiation, sort of, to related rates. So when you have two quantities that are related, you can relate the rates at which they change. And we did some of that in tutorial. And that's where some of the word problems come up that people are so mortified by. Okay. I'm not looking up that much, so if I don't see a hand, just shout it. Okay, we talked about modeling with derivatives, and we introduced differential equations in a very beginner sort of way. And then we moved on to a special case, exponential processes. So we talked about exponential decay and growth. We talked about half-lives. We talked about being able to relate half-lives to rate constants. We talked about examples of exponential growth and decay. And then we talked about that special example, exponential convergence. We did a little change of variable, and we managed to find out how a slightly unfamiliar differential equation behaves. We then talked about linearization and differentials, essentially as an approximation technique. But it also sort of led us to L'Hopital's rule. Coming off of linearization, we also talked about Newton's method, which, as I said again, is a root finding algorithm. Okay, so once you have a guess of a root, then you can use Newton's method to refine that guess. It's typically, when it works, better than the bisection method. It's faster, but it does fail at times. But again, it won't be tested on weird, crazy fail cases for Newton. Okay, again, then we went to determinate forms and L'Hopital's rule, which again you should only apply when it applies. Okay, and then we went into extreme values. Okay, so we look for local extreme values at critical points and at endpoints. know what a critical point is. It's where the derivative of the function is 0 or non-existent. We diagnosed critical points, so we could tell which one was a max, a local min, or neither, using the first or second derivative tests. And we led to that by understanding what the first derivative told us about how a function behaves. We then talked a lot about global extrema, okay, which come up when you're trying to solve real-looking optimization problems. So you want to find the biggest possible volume, the biggest possible yield, the smallest possible surface area, the smallest possible cost. So we did a few examples like that. And we saw boxes. Okay, so we talked about trying to maximize the volume of a box or minimize the surface area of a box. Variations on that kind of problem. Okay, the box could be open, it could be closed. The constraint could be on the volume, it could be on the surface area. The thing you're trying to maximize or minimize could be the surface area or the volume or something else. The setup could be different, so we talked about cases where you're just given material and you're asked to build a box, or cases where you're told to build a box in a certain specific way and with constraints on the dimensions, and you need to figure that out. I also mentioned very briefly a variation where the box, its parts, may be made of different things, and so what you're trying to minimize is not just surface area, but you're trying to minimize the cost or the weight of the thing. How would you do that? How would you construct a cost function and minimize that to get the best possible box? Remember that when we're trying to find global extrema for a continuous function on a closed domain, we can use the closed interval method, which is easy. We just look for critical points, we look for endpoints, we evaluate, and we compare, and that's it. When we don't have a closed domain, but we have a continuous function, we had alternatives. Okay, so we talked about the sort of variant of the closed interval method, which involved limits, as I mentioned earlier, and also global versions of the first and second derivative tests. Make sure you know when to apply tests, what they are, and practice on them. Okay, again, we talked about the behavior of functions, we talked about concavity, we talked about points of inflection, max, min, all that kind of stuff. Then we finally moved on to the integral. We started with the antiderivatives. We did some basic ones. We did higher order antiderivatives. Okay, you may remember the projectile motion example. We're going from acceleration to velocity to position. And we got arbitrary constants each time for which we could solve. Yes, ma'am?
Do you have to know sine H?
No, ma'am. Thank you for asking. Hyperbolic functions are not on this. For those of you who know what they are. And if you don't know, you can remain ignorant if you wish. We talked about sigma notation. So we could talk about Riemann sums, and we used Riemann sums to approximate areas under curves, and then we took limits and got exact answers for areas under curves. Yes, ma'am?
Are we giving trig identities on the?
Yeah, if you need, anything you need should be. Trig identities that you need should be there. Sir?
Do we need to know about slant asymptotes?
No. I don't think no. Oblique asymptotes or slant asymptotes are not tested. Not tested. Slant or oblique asymptotes. Okay, we moved on to the definite integral. We talked about signed areas. We introduced some rules, properties. And then we came up with the beautiful fundamental theorem of calculus, which let us evaluate a lot of definite integrals in a respectable sort of way. We used that notation to lead to the indefinite integral, its notation, its terminology, to talk about general antiderivatives. We talked about net change. Okay? Definite integral as an accumulator of change. So you should be able to understand that. And look at the examples I mentioned. Okay, finally, we came up with changes of variable to simplify integrals. Okay, so to make integrals look doable and to be able to solve them, both in definite and indefinite cases. And then finally, we talked about areas between curves. Okay, questions?
Do we need to know plus functions?
Of like derivatives?
Yeah.
Technically, yes?
Lovely.
Technically, yes. Yeah, you should. We didn't do that many, did we? The fact that we didn't do that many by first principles is a piece of hint. Yeah, derivatives by first principles, yeah, we didn't do much. Put it that way. Technically, it's possible, unless we say otherwise later. But we didn't do much, so how likely is it we'll torture you with that? Okay, some basic stuff can be done pretty easily. Harder stuff is damn near impossible. Okay, questions? We have a tutorial today. Come if you want. I'll be doing problems, as usual. We're done here, ladies and gentlemen. Thank you. It's been a pleasure. It's been a privilege. Thank you, thank you, thank you, thank you, thank you.